Hello and welcome. The following is the first in a series of lectures covering Chapter 44. If you ever learned about PET scans or CT scans, you'll know that radioactivity can be very useful, even if you got like a X-ray scan for your teeth. Radioactivity is a bit of a double-edged sword, but in this chapter we'll study the structure of the nucleus and we'll sort of start getting into why radioactivity happens in the first place. So, a nucleus is just a clump of protons and neutrons. The hydrogen nucleus is a weird nucleus in the sense that it's just one proton, but anything, any other element past that, it's at least, helium's at least two protons clumped together. So, beyond hydrogen, it does make sense to call every element, every atomic element having a nucleus. Anyways, so for a nucleus, we can talk about its atomic number, which is the number of protons it has, the neutron number, how many neutrons it has, and also the mass number, the combined count of nucleons, which are neutrons and protons. When we talk about elements, we usually just write the element symbol and the mass number besides them on top. If you want to be formal, you can also write the atomic number below the mass number, but the atomic number is kind of implied with the symbol since each element has a distinct number of protons. So fluoride at the bottom, for example, you do want to specify the mass number because it can have a different number of neutrons in its nuclei, but being fluoride, its place on the periodic table is ninth, so its atomic number is always going to be 9. So you can probably just write it as fluoride with an 18 on top only. And that tips you off that being fluoride, having 9 protons, then it must have 9 neutrons. So yeah, different elements can have different number of neutrons in their nuclei, and these form what's called isotopes. So every element has different forms where more or less neutrons and protons are in the atom. And for example, carbon has about 4 common isotopes, common in quotation marks, because the most common one is carbon 12, followed by carbon 13. And then there's more unstable isotopes like carbon 11 and 14 that are not naturally occurring, but they can be produced during reactions in a laboratory setting or by cosmic ray showers. The reason why carbon 12 is so much more common than carbon 13 is because it's more stable. Having an even number of neutrons and protons is desirable by nature. So here's a bit more info on each isotope of carbon, some of them anyways. The quick quiz here, you're comparing carbon, nitrogen, and oxygen. What do they have in common? If you look at their mass numbers, it goes up by 1, but so does their atomic number. Thus, they must have the same number of neutrons. This is asking about 3 different isotopes of nitrogen, so they must have the same number of protons because it's the same element. This is looking at nuclei where the mass number is the same, so they all have a different charge number, a different atomic number. So they also then have a different number of neutrons, so it all adds up to 14 for each. So they just have a total number of nucleons in common because the mass number is the same. So as for the sort of basic properties of the proton, its charge is that of an electron but positive. It's massive though compared to the electron. It's about 1700 times heavier than the electron. Its mass is shown here on the right. And the neutron, actually, its mass is very similar to the protons. It's just a tiny bit heavier, and heavier is relative because they don't really weigh that much. And neutrons being neutral, no electric charge, they were the last of the atomic particles to be found after the protons. I believe they were found in 1935. Now, if you want to actually measure the masses of atoms and nuclei and such, then in the same way that you can separate light with a spectrometer, where you use a prism to diffract light, you can use a magnetic field to um, basically shoot a magnetic field through an array of particles, and due to the charged nature of the particles, they're going to get deflected by the magnetic field, and the amount of deflection is proportional to their mass. So that's how you can tell particles of different masses apart, by measuring their deflection. Since overall the protons and neutrons are so not all that heavy compared to real world objects, then the atoms that they form are also not that heavy. We tend to use the atomic mass unit for their weights. And the atomic mass unit is defined that 12 atomic mass units are equal to the mass of one atom of carbon 12. So one atomic mass unit is about the mass of a proton or a neutron. This makes it a bit more kind of rescales the units of mass, so we're not always using such tiny amounts of kilogram to describe nuclear masses. Here's a Khan Academy video that talks more about mass spectrometry if you're curious about how you can measure the weights of particles. And here's a table talking about a few elements and the elementary particles as well, comparing their masses. So you can see that the electron is very light compared to the nucleides. And note the carbon atom. The carbon atom has an atomic mass of 12, and the atomic masses of the protons and the neutrons are a bit more than 1 U, but the carbon atom is 12 U, but 6 protons plus 6 neutrons would have a mass of more than that. So we'll address the difference in a bit. But I just want to point out the last column here. So this is stating the rest energy of the particles. And there's just a term here that's divided by the speed of light squared to just kind of acknowledge that it's not the rest energy needs a factor of c squared, right? It's not a mass. So that's what the term is there for. And it's stated in mega electron volts. So the rest energy, of course, the formula gives you joules, so it's just a conversion they do. Nuclear physicists like to work in electron volts because it's a sensible scale for particles. And yeah, like I said, the mass of carbon 12 in atomic units is 12U, but the mass of its nucleons separately adds up to more than 12U. The reason is that when the nucleons, when they're separate, but they join together, they are bounded and form a carbon 12 nucleus, they actually release energy. The nucleus is in a lower energy state than the constituents are when they're separate. So when they form, some energy is released. The other way around means that if you want to break a nucleus apart, you need to add energy. In the same way that to remove an electron from a atom, like the hydrogen atom, you had to add some ionization energy. Now, how big is a nucleus? Well, in Rutherford's experiment, or better said, the experiment that his students did, they were shooting alpha particles, which are just helium nuclei, so 2 protons and 2 electrons, into a gold foil. The alpha particles were getting deflected by the nucleus of the gold atoms. And they were actually able to figure out, using conservation of energy, that at some point, just before the alpha particles get deflected, they're approaching pretty close to the gold nuclei, and then they get deflected out. So with that, they were able to determine that the size of the gold atoms, or more specifically the size of their nucleus, must be smaller than the distance of closest approach between the alpha particles and the gold nucleus. And it's been better studied now, and it's been determined that the radius of an atom is roughly proportional to 1/3 of its mass number. So it follows the idea that no matter what the element is, no matter how many protons and electrons are in the nucleus, it takes on a spherical shape. So that's why the radius does increase with the number of protons and neutrons. But overall, then, if you just consider the size of a hydrogen nucleus, then its radius would be about 10 to negative 15 meters, which for particle physicists, they rather use the Fermi or the femtometer for that, which is 10 to negative 15 meters. And so to give you an idea then of how small that is, of 10 to negative 15 meters, that is a quintillion times smaller than the width of a strand of hair. And that's for a hydrogen atom, but even then, heavier nuclei are really not that much bigger than that. So these are very, 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 very tiny, tiny things. Interestingly enough, since we understand that the atomic nuclei do take on a spherical shape and that the radius is proportional to the mass number, then it turns out that for all elements, the density is more or less the same, since as more protons and neutrons are clumped together to form those heavier elements, the volume is also increasing. So there's a constant increase in mass, but also volume. So the density remains the same. So in this example, it's in the textbook. It's interesting because they talk about what the mass of the nucleus is, and that it would be proportional roughly to the mass number times the mass of a proton. Because the mass of a proton and neutron are so similar, so then the mass of a nucleus basically the total number of nuclides, of nucleons, times the mass of a single one. So for the volume of the nucleus, assuming that it does in fact have a spherical shape, then you can use the relationship between the radius and the mass number to get a formula for the volume. And then it does turn out that since the mass is proportional to the mass number, and so is the volume, then the density of an atom is unrelated to the mass number at all. It's more or less constant. So this is the density of an atom, which, as you can tell, it's at 10 to the 17 kilograms per meters cubed. So this is very, 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 very dense. That is a lot of weight packed into volume. So there's a cheeky part of the question here where you ask, okay, um, the Earth obviously is not as dense as a nucleus, but what if the Earth was this dense? So the Earth still weighs what it does, but now it's much more dense. So it's going to be a lot smaller. Well, how small is it? You can see here that its volume shrinks quite a lot, and that the radius of the Earth will now be just 180 meters to be a tiny, tiny Earth. Okay, so you might be starting to think, wait a minute, if the nucleus has a bunch of protons making it up, why don't the protons just repel each other out? What's keeping the nucleus together? And yes, there is this electrostatic force between the protons that makes them want to reject one another and pull each other apart. But there is another force happening not just between the protons in the nucleus, but between the neutrons with the other neutrons, the protons with the other protons, and the neutrons with the protons as well. This is the nuclear force, which, although very short range and relatively weak, it is powerful enough to keep neutrons and protons clumped together up to a point. Up to there's a certain limit on the stability, but it is good enough to keep most elements of mass of atomic number 83 or lower together. So basically, in a nucleus, you have protons trying to repel each other out, and that would make the nucleus unstable. But it's stabilized by the nuclear force that kind of keeps neutrons and protons glued together. And laboratory experiments have shown that between a proton and a neutron, or even between two protons, there's a low potential energy state that occurs when they're really close together. So this is a desirable state because you might recall in nature things like to lose potential energy. So once a neutron and a proton come close enough together, they reach this potential well where they're happy to remain here. Kind of like a ball that falls into a pit. The ball's going to want to stay here. For the proton-proton system, there's a bit of a hill to get to the sweet spot because of the Coulomb repulsion. So the Coulomb repulsion, which is the effect of the electric force, has a much longer range than the nuclear force and want to keep them together. So as two protons are approaching one another, there's some electric rejection. But if there's enough energy to overcome this little hill, then they'll be close to enough to each other to interact in terms of the nuclear force, which at this point is stronger than the Coulomb repulsion and gets them to this low potential state where they'll be happily joined together. However, as more protons and neutrons combine to form heavier nuclei, at some point the Coulomb repulsion is too strong that the nuclear forces just cannot keep the nucleus held together. Because of the short range of the nuclear force, only neighboring nucleons in the nucleus can really have a nuclear force effect on each other, which means that for a really, really big nucleus, while only neighboring protons and neutrons are gluing each other together because of the nuclear force is such short range that only your neighbors can hold you down. The Coulomb repulsion, though, the electric force being much longer range, means that all the protons in the nucleus are trying to tear each other off. So that's why for heavier nuclei that have more than 20 protons in their nucleus, their stable forms, so elements with atomic number of 20 or more, their stable forms usually have more neutrons and protons. As you can see here, this is showing you the naturally occurring isotopes of elements in nature. And this line here shows you where the number of protons will equal the number of neutrons. But as you can see, as you go up in atomic number, most elements end up having more neutrons than protons. Basically, to compensate for the increasing effect of Coulomb repulsion, more neutrons need to be added to keep the element stable. However, at some point, which is at elements beyond an atomic number of 83, no matter how many neutrons you add, you get diminishing returns on the glue effect of the nuclear force, and the Coulomb repulsion between the protons is too strong that the nucleus is unstable and is prone to radioactive decay. So we'll talk about radioactive nuclei later in section 44.4. Anyways, that's all for now. I hope you join me next time.